Okay, hello again. I hope that paint will not be as problematic as this journal was. So let us go further. So we spoke about, I remind you that we spoke about various branches, various modeling options for non-cooperative game theory. And we said that, so let us divide this for game theory per se, and here we had mechanism design. So we started with non-cooperative when we actually explicitly model the strategies, and for each profile, so for each set of strategies, so I do that, he does that, he does that, we have some result. That's the idea of non-cooperative. The basic, in my opinion, the most intuitive way to model something. And the other way is extensive form. Here we don't just talk about strategies as abstract entities. So I can take this strategy, and if they take their strategies, that's what we get. No. Here we concretely model what a strategy means, and we say that a strategy is how I behave at each and every step of the interaction, and we model this by a tree. So in the beginning, let's say that I act and I have three options, so I drew those three options. Let's say if I took this route, I denote it by 1, that's simply for notation. Then, so if you I, then you have Joe acts, and he has two options. If I took this route, then you have also Joe who acts. But if I took this route, then I have Mary. She acts, and she has 4 options. And so on. So we can exactly denote who acts at each situation and what are the options of that person. And the strategies are how to exactly act at each situation. This allowed us to talk about things like what we remember, how we got to a certain point, whether we know what the other person did, and so on and so forth. So this model allows us to tell much more than when we look at strategies generally, but of course it comes at a cost. It's usually more complicated. So both strategic form and this called extensive form, both forms are important, and they are both classical forms to talk about non-cooperative games. And as I said, the same game can be modeled in several ways. Now, on the other hand, there is a way to think about games which actually tells these games, for example, fit that and those not. For example, there is a notion of zero-sum game. That when you have two people, and whatever they do, let's talk about just two people because that's an interesting case of zero-sum games. If whatever they do, the total, let's say, the total amount of money they earn is the same, that means that they have a pure competition. So whatever I earn, he loses, and the other way around. So this is a very important kind of games. And some games are like that, some games are not like that. Of course, we would like to believe that we can always enjoy together and we don't have to have this competition, that I can only get something at someone else's expense. But some interactions are like that. For example, if we model attack and defense, of course, there is definitely a competition, so it does not actually have to be zero-sum. But that's an example of a competition. So there are also, let me just write kinds of games. For example, zero-sum games, or in general constant sum, so that the total, let's say, amount of resource is the same, and the question is only how you divide it. constant sum. Another interesting kind of games is potential games. We're going, I think, to have time to talk about this. Potential games. Now I'm just going to tell you the intuition. The idea of potential game is kind of the opposite of zero sum. You have something called potential, which represents your common inspiration. So you don't have to be opposed to one another. You can find some common inspiration. That's very important, and if you do have this, that says that usually you have a Nash equilibrium if this is finite, and again, it's a bit jumping forward, but what it means that we have a stable state, so this is also a very important thing. Another thing we can talk about is, for example, determinate and non-determinate games, and of course that starts being really determinated or not. So if you have a game, and we are going to talk exactly what we mean by a game, but now I'm giving you a flavor. So if you have a game and you can maybe show that an agent always can win by acting in a correct way, regardless what the other person does. So an agent has a so-called winning strategy. That means that the game is determinated. Otherwise, it is not determinated. In many simple games, it's possible to prove that it's determinated. For example, if you just kind of tree like I drew here. But in many cases, much more complicated cases, when, for example, you don't have full information, you don't know exactly how you got to some situation, then it can be non-determinate. Okay, so this all was for non-cooperative games. And let me see whether I've forgotten to say something about non-cooperative games. Okay, let us now talk about cooperative games. So cooperative games, let me think. I'll just continue this idea. So in the left we have this game theory, and cooperative games, they model the set of agents, set of players who play. Let's say you have 1, 2, 3. Those are the names of 3 companies on the market. And you can model what each coalition is able to achieve. So if company 1 and company 2 comes together, then let's say they are able to achieve 10 units of profit. If company 1 and company 3 come together, then they're able to achieve 12 units of profit. If all the companies come together, then they're able to achieve 25 units of profit. For example, for each coalition, saying what they are able to achieve, that is the natural, the straightforward way to define such a cooperative game, and that's called the characteristic function form. So you have a function which gives the value of each coalition. So for each subset, so set of all the subsets from this set, this goes to real numbers and tells what each coalition is able to achieve. Now, this is definitely fully expressive, but it, of course, is very inefficient even to write this. So when we want to talk about algorithms, for example, you want to write the same information in a more efficient way. In some cases, it's a good idea to write, for example, using a rule. So we can say if agent 2 is present and agent 3 is absent, then that's what happens to the value. Another rule is if agent 2 and 3 are not together, then something else. So there are several ways to define cooperative game. So we can define them by characteristic function, or these are not the only ways, but let's just name those two, or by rules. So if a certain rule takes place, then you can take 2 more units to the aggregated value which you count. And this was just a way of modeling. Now, cooperative games also differ by how they actually are. So not only by how you choose to model them, but by how they are. And for example, we can have cooperative games which are with transferable utility or without transferable utility. So what does it mean? So if a game is with transferable utility, transferable, it means that the value of the coalition can be divided in any way between the agents who constitute the coalition. If it's without transferable utility, for example, money is transferable, but for example, your enjoyment from being with a certain person in a bus when you go to some trip is non-transferable. Because if someone else enjoys being with Jack, it does not help you. So it can be either with transferable utility or without. Now without means that you cannot transfer utility arbitrarily, but maybe you can have several options to divide the utility between agents. So without, it requires further specification. And we are not going to talk about games without transferable utility because it's quite more elaborate, quite hard. Okay, another thing I may have forgotten to tell. There are many ways to also tell something about the game. So there are, for example, games where the value function, the function which basically defines what is the value of each coalition, which goes from the set of all the coalitions to real numbers, it can be, for example, either sub-additive, additive, sub-additive, or super-additive. It does not have to be either of those, but it can be. Additive means that if you have 2 coalitions which are disjoint, that was what this dot means, then the value of the unit is exactly the sum of the values. And that's what it means additive. Sub-additive means that it's like that, and super-additive means it's like that. And sometimes we can prove that for such and such class of functions, we can calculate something. There are also other interesting ways to look at those functions. We can also talk about supermodular and submodular, and here the question is, if you add another player to a coalition, is it better to add a player to a larger coalition or to a smaller coalition? So, for example, let me go. I draw this line to show that all this goes for game theory, and we still have to go to mechanism design. So for game theory, we can also talk about sub or super modular, and here it means that if I, for example, look at the value of a given coalition T united with the singleton made of agent X, and I compare the value we have to the value of the coalition T alone, is this growth because of X going to be larger or equal? Is it going to be equal, or is it going to be smaller or equal to the growth that another coalition S would have undergone from the same agent when we assume that T includes S? We can even say that it includes, strictly includes S. Includes and is not equal. And here you have also this sub and super modularity, but again, I'm just giving you possible ways to define classes of those characteristic functions. I'm not telling anything about what are the conclusions. These are simply reasonable classes, because sometimes you can definitely say, if you, for example, add another team member to a larger team, often the larger the team, the less useful the new team member is, because anyhow the people already know what to do without that person. But in some cases you actually can have synergy, and then the more people you have, the better is to add someone else. So you have reasonable ways to motivate why certain functions are sub or super modular, and you also have this idea of additivity. You can talk about why you have additive, sub or super additive functions, but I'm not telling anything about what actually the conclusions are. Okay. Now let us talk about mechanism design. So first of all, what is the difference between mechanism design versus implementation theory? These are, by the way, are topics we are not going to deal with in this course. I'm just giving you some flavor. So mechanism design is when you want to get, so mechanism design designs, sorry for the tautology, a game. For example, it designs the laws of the country such that such that a desired behavior will take place. So one of the good options has to be well motivated in this game. It has to be okay to be honest, for example. And it also often requires that, for example, I don't know what exactly your values are. I want to design an auction such that you are motivated to tell me the true values, and then the auction gives the item to the person who values it more. That is an example of a mechanism design problem. Now, implementation theory is, I can say it's a bit less practical, it's a bit more theoretical. It says, okay, what can we implement as a certain equilibrium? I'm now telling this assuming you intuitively understand what it is. Of course, it depends on the definition, and we are going to talk about that. What can be implemented as a certain equilibrium? So, which functions can we have well motivated by some kind of game? It's a very mathematical question. It's less practical if we just want to optimally allocate an item and we want people to be honest. That's the more practical question that we have in mechanism design. And that's why I think mechanism design is more often studied than implementation theory, though of course they are very, very much related. So it, for example, can ask which behaviors can be obtained in stable state of games. And now let us just assume I'm wiping this whiteboard. No, it does not let me. Okay. And there are many topics about that mechanism design. For example, many kinds of auctions. So we want to design examples. They're even not examples, they're more like domains of study. So we want to design an auction of a certain kind, so that people play in a certain way, such that people will give you their true preference and you will give the item in a way which is optimal for the society, for example. So the domains of studies can be auctions, and auction theory is a very broad theory, so it's definitely a very broad thing. Auctions, it can be voting, which voting system will motivate people to vote honestly, and not saying, I just want that person, but that person will not will not win anyway, so I will just vote for someone else. So there are voting systems which also motivate people to vote honestly. Also norms, societal norms, of course. In an efficient society, they also motivate people to behave in a socially useful way. And also laws, of course. So which laws will motivate people to behave in a way that we want them to behave. Okay. So they also give some areas which are, I would say, just related to what we just did. So for example, epistemic game theory talks about what can be known and how knowledge influences how we play. So other related areas. Epistemic game theory, it's about knowledge. Now logic and game theory for example, how can you basically logically, using the tools of formal logic, express knowledge, express what an agent can do and all that. And that of course can help you calculating stuff. Another thing is algorithmic game theory. Now algorithmic game theory has at least two ways to look at it. So first of all, if you have a certain behavior, a certain rule by which robots behave, this defines the game. So rules, algorithms, define a game. And also, given a game, we can look at how can we find some equilibrium in this game, which we have not yet defined. So we can also ask algorithmic questions about the game. And algorithmic about a game. So there is definitely a strong interaction between those two areas. Now let me see whether I've forgotten to tell something else. I've already talked about evolutionary game theory, so when you basically look at strategic or not, often non-strategic interaction between some, let's say, animals, you assume that those who are more successful give progeny, so they have more children, they have more succession, and then you look at the whole process. So this process definitely depends on interaction, and that's called evolutionary game theory. If you've read The Selfish Gene by Dawkins, he speaks a lot about that. He writes also about Maynard Smith. I think Smith got the Nobel Prize also. So that it was quite a prolific interaction between the two domains of evolutionary biology and game theory. And sometimes game theory can explain why, for example, certain behaviors which can seem useless or at least unclear why people or other animals use energy on those, why they can be useful. For example, it does not seem that the peacocks, the male peacocks which have large tails, are using their energy in the right way to grow such tails. But the evolutionary game theory explains that okay, maybe the females choose those who have large tails because that demonstrates that they are healthy. And there are many details and there are many theories, and from what I know it's still not clear exactly how this works, but I'm simply giving you this as an example that is definitely an interesting thing. So the last thing I want to say is that there are many other applications of game theory. It can be war, it can be economical application, it can be interaction between colleagues, anything can be usually modeled as a non-cooperative game theory. Cooperative game theory, which looks at coalitions, often models games in a parliament, or how you form a team, and so on. And application of mechanism design, as I said, it includes basically so-called preference aggregations, which means taking the preferences of many participants and giving a decision which somehow reasonably represents all those preferences. So of course voting is the most famous example, but also which laws to make. It's sometimes the case that politicians make law in order to get something. They say they want to get people work and have less unemployment rate, and they want to have, so they say, okay, let us force the employees to never be able to fire a person for certain cases, for certain behaviors. But in reality, that sometimes causes employees actually to be afraid of taking a person to work at the first place. So the result of a law is often hard to predict. And that's definitely a domain of mechanism design. And one last thing which I will tell in this general introduction before we move to the utility theory is that we take a normative approach here. What it means is that let me write it down. We take a normative approach. We assume a certain way of behavior, rational agents, those preferences, and we deduce how the agent should behave. We don't look at how the agents really behave. Of course, the descriptive approach, how the agents behave, guides us, but the main approach we take is normative. Okay, now let me pass to the new topic, which is still in the introductory part of the course, and that is utility theory. That's a theory which underlies game theory.